anyway, I got through my classes with excellent grades, always getting those circuit problems right, never really knowing what was going on in those circuits. And it wasn't until I went to work with Lillian McDermott that suddenly I was able to build this model, a gut level model that helped me understand what was going on in the circuit and make them obvious. And that's what I want to give to you. But not today, okay? Not today. Today's going to be just a standard lecture on Ohm's law, a lecture that you might get at any one of those lesser universities like Harvard or Stanford. And that's because I'm ready. You're not ready. You need to watch that video of the tutorial before we can have the discussion that we need to have and to start learning the way it needs to be learned. Now you'll notice that on your schedule, we have on Wednesday, tomorrow, this watch tutorial 4. When we were thinking we were going to have in-person tutorials, all of your little breakout sessions were, I think 90% of them were on Wednesday. And everyone had their breakout session before they came to Thursday class. And that forced you to have the experience when you needed the experience. Well, this time I'm just asking you, please, get that tutorial experience before you come to class on Thursday, if you would. It'll make so much more sense on Thursday if you do. Let's go ahead and start with prayer. Good brother, you're standing up. Would you offer a prayer for us, please? Sure. Thank you.
For dear, kind and gracious Heavenly Father, we're thankful for this opportunity to meet together for the physics. We're thankful for Dr. Francis' preparation. Please help us to be attentive that we may learn effectively. These things in the name of Jesus Christ.
Amen. Oh, I just want to quickly say that last Thursday evening, they released the course evaluations for last semester. And I was able to read what you said about me. And so now I want to tell you what I think about you. You are wonderful people, and it's not your fault. I blame your parents. Okay, you have wonderful parents that raised you right, and it was very kind and gracious, the things that you said about me. Not much of it was true, but it was kind. So let's start fresh here. And okay, that's broken. Out with the old, in with the new. Okay. Let's start with just a basic idea like a flashlight. You've all had a chance to take a flashlight apart, and you know that inside you got batteries, and they're often stacked, positive to negative like that. We call that in series. And then there's a bulb that glows, and there's a switch. And these are connected with wire, a conductor, so that when I move the switch, I close that gap and I complete what we call a circuit, or a complete path from one side of the battery to the other side of the battery. Now, we draw this in what's called a schematic diagram, where we represent the batteries with this symbol we've seen before. the filament in the bulb, we're gonna find is a resistor, and we use a symbol like that to represent resistors, and then a switch we represent with that simple symbol there. Now, I'm starting simple, but it's just, you know, a couple of days, and you're gonna be working problems like this, where I give you 7 identical bulbs, flashlight bulbs. When I say identical, that means they were made at the same factory on the same day by the same worker. His name is Sven, okay? And so these bulbs are completely the same. And I hook that up to a battery, and I ask you, which of those bulbs is brighter? And some of you will say, well, they're all identical bulbs, Greg, so they'll all be the same brightness. And that would be worth 0 points. Okay, because they're not. They're not. 1's gonna be the brightest, 7's gonna be the second brightest, 6 is gonna be the third brightest, 2 and 3 are gonna be tied for next, and 4 and 5 will be tied for last. And that's just gonna make sense to you once you have this model. You're not gonna be able to see a circuit like that without understanding what's going on. So before we get there, though, let's see where we are. Let's take a pretest. This pretest has been given hundreds of thousands of times all over the world. One of the most famous pretests in physics. And what we're going to do is we're going to take 5 identical bulbs, and we're going to hook them up in 3 circuits. Each of those circuits has a battery that's identical and ideal, okay? And the question is, which is the brightest bulb, which is the second brightest bulb, and so forth. And these are your choices. We're going to use our clicker to take this pretest. Just hold on and I'll get you started. Now you can click. But I would think before I click, okay? I would not just click. I would do some thinking. Now, it may be that some of you that are in the 108 class have already gone far enough in circuits that this is obvious to you. We'll find out in a moment.
Wait, Greg, is the voltage the same on all the batteries?
They're identical batteries.
Yeah.
Yep. As a matter of fact, they're 6-volt batteries. Yes, they are. Okay, last call. Get your vote in. Okay. Okay, good. Good. But we see that we're not all in agreement. But we did much better than a class that had not had 108. Evidently, 108 is working for you. This test has been given all over the world, as I said, and often, most often, it's given after traditional instruction, after lecturing and reading the book and all of that. And what we find over and over again, regardless of whether we give this at Harvard or whether we give it at Montana State University, is that 10% of the students get this right with the correct reasoning. If you go to a calculus-based class, the engineers, they do much better. 15% of them get it right. Okay. And once Lillian McDermott was giving us a workshop at a big conference for science educators. There were math professors, chemistry professors, physics professors, all the geeks were there. And she gave this pretest, and they nailed it. 17% of them got it right. So there are a lot of misconceptions that people have about circuits. And if I had asked you to flesh out your reasoning of why you chose the ranking that you did, I bet that some of those misconceptions would come to the surface. Now, let's talk about this idea of current. You've used the idea of current in your everyday language with other people. What it is just a measure of the rate of flow of charge. If I were to draw a big red line right here and put a folding chair there and get one of those little counters that the Walmart greeters have and just count how many coulombs go past that red line in a unit of time, that would be the current, okay? The definition, we use capital I for current, historical reasons, and it's just the amount of charge divided by the amount of time. Now, I've told you over and over again that whenever you have a definition that is a ratio, something divided by something else, make the basement 1, okay? Set the basement equal to 1, and that will tell you what's going on. It's how much charge goes past that line in 1 second, okay? And I told you before, that's why we got such a large unit for coulombs, is because the amp it was defined first. And an amp is a reasonable amount of current. If you've got something going in your kitchen, you know, a blender or something like that, it's going to have about an amp, a half an amp going through it, and that's reasonable. But because of that, we have a coulomb that is so huge that it's dangerous, and we just live with that. Now, it turns out that Ben Franklin had a 50-50 chance of getting the whole positive and negative thing right. And it was just an unlucky day. It was just an unlucky day. And we've been paying the price ever since. And so it turns out we can show that the current is actually a flow of negative charges through the wires, through the conductors. But we, as you know, really don't like minus signs. We've got a bunch of minus signs in physics, and you know that every time we have one, it causes you grief. And so we have gone out of our way to get rid of as many of those minus signs as possible. And so we use what's called conventional current. And what that means is that we find that for all intents and purposes, there's no difference between electrons flowing to the left or positive charge moving to the right. Okay? Now, there's one experiment that can tell the difference between those, the Hall experiment, but we're not going to do that. And it's not easy to do. So, you know, what we're going to see is that there's nothing that we can observe with our eyeballs that's telling us whether the current's going from the positive terminal of the battery to the negative or from the negative to the positive. And so what we're going to always do is talk about conventional current, which would be the flow of positive charge, make believe, from the positive terminal of the battery around to the negative terminal of the battery and through the battery, okay? Now, it's not just physicists. We're not the only geeks that are doing this. The electrical engineers do that. Every scientist does that. And indeed, if you talk to an electrician who's fixing your home, they talk about conventional current as well. It's just us making up for Ben Franklin's mistake. Okay, how do we measure current? Well, by the end of today, I'm going to have a car battery here. The department was very reluctant to have a car battery because any of you that have worked on cars know that there's ways that you can hurt yourself with a car battery. And for some reason, they think I'm undependable. But I promise them that all of those mistakes that you can make with a car battery, I have made. I know what those mistakes are. Okay, so this is taking the place of the car battery. It should be set about 12 volts, 12.1. We're getting a little extra there. And to measure current, we use something called an ammeter. And an ammeter has to be inserted, we call it in series. In other words, I have to break this line, turning off the bulb, and shove that ammeter into the circuit. So what I'm going to have to do here is I'm going to have to, oh man, these guys are not helpful. So I'm gonna break this line, and I am going to shove this ammeter in so that it, now the current has to go through the ammeter and then through the bulb. Okay, and you see that, look at the brightness of that bulb. Okay, now without the ammeter, look at the brightness of that bulb. Yeah, now you can't see anything, right? You got that big old blind spot now. You don't want your measuring device to change the thing that you're measuring. I don't want that to suddenly have less current flowing when I put in the ammeter. And that tells you something about ammeters, how easy it is to get through an ammeter. And we'll talk about that in a little bit. Now, what drives the current? What's causing the current to flow? Well, that's the electromotive force, or the EMF. And this is another great mistake that was made by those that went before me. Indeed, my friends one day gave me for my birthday an ancient physics textbook that was written not for students, but for instructors. And it was written by a prominent physicist. And the chapter on the electromotive force started by saying, tell your students what it means very quickly and hope they forget. Because it's not a force. It's misnamed. It's poorly named, okay? This electromotive force is just the battery. It's just the battery pushing in a way that looks like a force, but what it really is the amount of energy that each 1 coulomb gains as it goes through the battery, as it goes from the negative terminal of the battery to the positive terminal of the battery. If it's a 12-volt battery, remember what volt means. Volt means joule for each coulomb. So the battery chemically gives to each coulomb that goes through it 12 joules of electrostatic energy. Now, when those coulombs get through the battery, they're not just all hyper like they've just had a Coke. You know, it's not that kind of energy. It's the type of energy like the boulder at the top of the cliff. You know, it's not jiggling around because it's got a whole bunch of energy. It's just waiting there to get to the bottom of the cliff, okay? And in doing so, it's going to acquire kinetic energy. Now, we'll just call this the battery voltage, okay? And that's what we're always, the language we're always going to use, but sometimes we'll use this symbol. It's historical. It represents the name electromotive force, or EMF. We use that curly E or epsilon. Okay. Now, if I think of that battery as a pump or an energy source, if I were to measure the voltage And when I say voltage, have we all figured out that that's shorthand? When I say voltage, what I mean is voltage difference from some point A to some point B. And if I measure voltage from the negative terminal of the battery to the positive terminal of the battery, and it's a 12-volt battery, I get 12 volts or 12 joules for each coulomb. And if I were to measure the voltage difference from C to D, what I would get is a voltage difference of negative 12 volts. Okay, and I can interpret that as energy being given to each coulomb as it goes through the battery, and then losing or giving up that 12 joules of energy for each coulomb in the bulb. Now, it doesn't lose the energy, it just converts that energy to heat, light, other forms of energy. Now, this is the cartoon that I want running through your head. Physics is all about finding the right cartoons that just explain in a simple way what's going on, okay? And so what I want you to see there is each of those circles represent a coulomb of charge. And the darker they are, the higher the electric potential energy they're at. The dark red ones are at the top of the cliff. The light red ones are at the bottom of the cliff. And as we watch this, you can see these coulombs go around and dump their energy at the bulb. But I don't use up the coulombs. Okay, the coulombs are well, they're really electrons. We think of them as positive charges, but they're particles that can't just disappear. And so if I were to put an ammeter there and there, what I would find is I'd get exactly the same reading on those two ammeters. And the way I say this is what goes around comes around. Okay, it's like gossip in a small town. What goes around comes around. It doesn't get used up. It just keeps on going around, round and round, round and round. Now, in that way, you can think of these circles, these coulombs, as little dump trucks. You know, they go through the battery, they pick up their load, they go to the bulb, they empty their load and go back for more. Okay, but it's energy that gets converted or transferred into a different form, not the coulombs. Miriam?
If I broke the circuit, would everything stop?
If you what?
If I broke the circuit, like if I
Yes,
just like break something out of
if
the
you-
battery.
If you opened a switch in that circuit, it would stop everywhere at once. I would always have the same reading at one point in the circuit as I would at the other for a simple circuit that doesn't have several branches. We're going to get into more complicated circuits that branch out in just a little bit. Scripture for the day, Ecclesiastes 1. The wind goeth toward the south and turneth about unto the north. It whirleth about continually, and the wind returneth again according to its circuits. All the rivers run into the sea, yet the sea is not full. Unto the place from whence the rivers come, thither they return again. This idea of a complete circuit, everything goes back to where it started and starts over again. Okay. You should still go to the devotional. Okay, that's not enough. Okay. Now, how do we measure voltage? Well, we use a voltmeter. Now I'm going to get rid of this ammeter and I'm going to bring up a voltmeter. And some of you are saying, whoa, Greg, that looks a whole lot like the ammeter. And indeed, a lot of the internal guts of it are very much the same. What is different about it is its internal resistance, and we'll talk about that in a moment. Now, how do I connect a voltmeter? Well, to to answer that, let's remember that when I say voltage, and when I'm trying to measure voltage, what I mean is voltage difference from some point A to some point B. So I'm gonna think of these leads here as danger, danger, Will Robinson. You don't know what that means. I'm gonna make this go at point A and this go at point B. Okay, and so that means I would be connecting this in what we call parallel. Now, let me get this glowing again. Get rid of the. Let's see, get rid of the ones I don't need. Okay, so I got a 50-50 chance of getting this right. I'm either measuring from C to D or D to C. I can't remember. But you notice I'm not that worried because there's really no way I can damage this. Did I get it right? I did not. 50-50 chance, me and Ben. Okay, so let me do it the other way. And you see that it measures about 12. Okay. Now, that tells me something about voltmeters. Okay. As the current flows around this circuit, I don't want the voltmeter to drastically change what I'm measuring. I'm trying to measure the voltage across that bulb, and I don't want to change the voltage across that bulb by measuring it. And so what happens is that we construct the voltmeter so that it's really, really hard to get through. It has a huge resistance, internal resistance. And so if I had 10 amps coming from that battery, essentially all of it still goes through the bulb. And only a tiny trickle goes through the voltmeter. And then the voltmeter uses some physics that we will learn later in the semester dealing with magnetic forces to measure the voltage. If it takes 0.001 coulombs, and we measure that the change in potential energy for that is a negative 0.012 joules, then we just use our operational definition of the change in potential energy divided by the test charge, and we get the voltage, or negative 12 volts. Okay, so in summary, an ammeter that measures current or the flow is put in series, in line. We have to break the line and shove it in. But a voltmeter that measures the push, that we add in parallel from point A to point B. Now, consider a simple circuit. If I increase the push, you know that's going to change the flow. The push is what causes the flow. And you know that if I hook up a bigger battery, I'm going to get a brighter bulb. I'm going to get more flow. Okay. You also know that if you go down to the hardware store, all the bulbs are not identical. You got 10-watt bulbs, 40-watt bulbs, 100-watt bulbs, 60-watt bulbs. Okay. And so we can change the bulb. And the difference between those different kinds of bulbs is the resistance. Not all identical pushes produce identical flows. So let's talk about resistance. What's this? Resistance is futile. That's the board, right? Okay. Don't know anything about science fiction? Okay. Resistance is futile. Resistance represents the ability of a circuit element to impede or obstruct the flow of current. And the operational definition is just the voltage divided by the current. And again, when you've got a definition that is a ratio, something divided by something else, set the basement equal to 1. If I wanted to know the resistance of this pen, what I would do is I would set up a voltage difference from one side of the pen to the other side of the pen with some power supply that I could turn up the voltage, and I'd keep cranking it up and cranking it up until I got 1 amp going through this thing. And then that would be the resistance. That would be the definition of that resistance. How much voltage I would need to make 1 amp go through the element. Now, we use the units volt per ampere, the ohm, again to represent a dead physicist. In this case, it's Georg Ohm. And I just got to point out, one of the very few handsome physicists, okay? That is a good-looking man. Now, many objects, many materials are what we call ohmic. And that just means that regardless of how much current we have going through them or what temperature they're at, their resistance stays the same. And in that case, we treat R as a constant. And this becomes what we call Ohm's law. And Ohm's law is the F equals MA of this part of the class. That's it. That's it. Now, I want to emphasize that. When I was an undergraduate here at BYU, many years ago, before your parents were born, okay? Dinosaurs were roaming the campus. We had a class of physics majors that there were 12 of us. And we just went from class to class together. We took all the same classes together. We knew each other very well. Until we got to the senior quantum mechanics class. And then there were 13 of us in there. And that was because there was a young man named Eric who had been a physics major for many more years than 4. And the problem was he could never get through this quantum physics class. And he just kept trying. And the physics department wasn't real excited to get him through that quantum mechanics class because he was in charge of their electronics repair shop. And anything in the department that was electrical, that was broken, they would bring to Eric and Eric could fix it, no matter how complicated. Well, we took it upon ourselves to get Eric through that class. We were going to make sure that he graduated. And so I was working with him one night on homework, and I was explaining things, and I was trying to make it just as simple as I could. And Eric just wasn't getting it. And I was getting frustrated because it just seemed so easy to me. And finally I said, Eric, it's not that hard, buddy. It's not that hard. What you do in the electronics shop, that's hard. This isn't. He says, "Aw, shucks, Greg." He was from Tennessee. "Aw, shucks, Greg. Electronics ain't hard. Something broken, you fix it just by shaking your finger at it. V equals IR, V equals IR, V equals IR." That kind of broke the tension a little bit, and I laughed. But over the years, I've come to realize that Eric was right. When you get a problem on your homework or the exam, you just shake your finger at it. And V equals IR, V equals IR. But you got to know which V and which I and which R. Okay, if you truly understand Newton's second law, you really know what the net force is and how it affects the acceleration of a mass, then all of those problems on that test in 105 were just F net equals MA, F net equals MA, F net equals MA. It got boring. Well, that's the way it is with these circuits. If you understand that equation at the same level that you understand F net equals MA. Okay, let's talk about resistance. You've got some gut level understanding of resistance. If I had two cylinders that were the same dimensions, one of steel and one of wood, which has more resistance? Shout it out. Wood, yes. What if they were both steel, but one of them was longer? Which has more resistance? The short one or the long one? Shout it out. The longer one. You can think of that as two straws that you're trying to blow air through, one short and one long. It's going to be harder to get the air through the longer straw. Okay. Now, what if I have two that are the same length, but one's fat? Okay, one's got a big diameter. Which one has more resistance? The skinny one or the fat one? The skinny one. Okay, again, think of the straws. You got a skinny straw and a fat straw. It's easier to get the air through the fat straw. Now, the formula for that should make some sense is that the bigger I make the length, the bigger I make the resistance. The bigger I make the area, the area cross-sectional area, the smaller I make the resistance. Does that make sense? And then this rho, this Greek letter rho, that we call the resistivity. And that's just a constant that's different for each material that tells you how hard it is to get through that material. That's why you said it was harder to get through the wood than the steel. And so things that are easy to get through have a small value of rho, like copper or platinum or silver would have very small values of rho. So with your clicker, is the earth a good conductor? Yes or no? Now you can click. And if I could just put in an advertisement. If ever there was a lecture not to miss in 106, it would be Thursday's lecture, okay? That would not be a good one to pass up. Okay, last call, get your vote in. Is the earth a good conductor, yes or no? Okay, the answer is yes, a good conductor. Now, the key here is the word the earth. Earth, meaning dirt, is a poor conductor. Trying to get current to go through a bag of dirt is hard, okay? It's just very resistant. But the earth acts like a huge copper ball. And that's because if I look at that formula, the resistivity of dirt, that's high, but the area is humongous. If I were to put a stake in the ground here in Provo and another one in Salt Lake and measure the resistance between this stake in Provo and that stake in Salt Lake, I'd get negligible, I'd get nothing. And that's because there are so many ways for current to get from this stake in Provo to that stake in Salt Lake. The cross-sectional area is so huge that the earth acts like a big copper ball. And often when we want experiments to give us the same results or results that we can compare to each other, we do what's called grounding it. We take the negative terminal of the battery in our circuit and we hook it to some pipe that's going down into the ground, some metal pipe like a sink that's going down into the earth. And then we know that in a metal, the electric field is zero, so the voltage is the same. And so that means if if I've done that to my experiment here and you've done that to your experiment in France, we have the same reference point of 0 volts at our negative terminal of our battery, okay? Now, let's do another clicker question. What is constant for a battery? Is it voltage, current, or both with your clicker? Okay. Let's get her done. Good, 108 is working. It's voltage, okay? When you buy a 6-volt battery, that label 6 volts is the brag. I'm gonna give you 6 volts, come heck or high water. And most batteries don't live up to that promise, okay? Most batteries try to give you 12 volts, come heck or high water. But sometimes the chemistry just can't keep up with the demand. I think those of you that have worked on cars know that you can take a car battery and you can grab the terminals with your hand and you're fine. You're not gonna feel anything. You've got enough resistance in your body that 12 volts is not gonna push any current that's gonna be felt by you, okay? But if you were to take a wrench and accidentally put it down from the negative terminal to the positive terminal of a car battery, everything goes crazy. There's sparks, there's heat. Usually it gets spot welded to the terminals and then you have an explosion, okay? That only happens once. And that's why the department doesn't want to buy me a car battery. Because they're afraid that I'm gonna make that mistake. Now, I did make that mistake in Montana. What I did is I had the car battery hooked up and I disconnected the bulbs and threw the wires down onto the table. But I threw them down. I mean, if I was trying, I couldn't have done this, but accidentally they fell on each other. And now there's a table with a great big scorch mark all over it. That was me. That was me. So now, whenever I'm dealing with a battery and I want to disconnect it, I disconnect it at the battery and throw it down so that we're safe. Now, if I look at Ohm's law, when I say V equals IR, what I really mean is delta V of the battery is equal to IR. And so if that's a 6-volt battery, then what that means is that it will always push with 6, think of volts as the push driving the current. And it will always push at 6 volts. And V equals IR tells me that I'm going to get 3 amps going through that battery because 3 times 2 is 6. On the other hand, if I hook that same 6-volt battery to a bigger resistance, a 12-volt battery, I'm sorry, a 12-ohm resistance, what I get is only a half an amp. It's pushing the same, but it's just harder to get current around that circuit. And so I get less current. Now, if instead of 2 ohms, I just put something that has a very small resistance, like the wrench or a wire. Well, now, if you put 0 in for R and 6 in for the voltage, what does I become? Yeah, infinite, okay? And it turns out that as you hook up something that's very, very low resistance, the current has to get very, very big if the voltage is going to stay 6 volts. And the chemistry often can't keep up. Now, a NiCad battery, the type that we were using in that tutorial that you'll be watching, they are very good about supplying lots of current very quickly. An alkaline battery, they're cheaper and they're not so good. You hook them up to something that's very low resistance and they will very quickly just roll over and give up and just say, can't do it, can't do it. Okay. Now, because of that, if you take a NiCad battery and you hook a wire from one side to the other side and hold it with your fingers, you're going to burn yourself. That wire will very quickly get so hot that it will actually melt the plastic coating right off the wire. Whereas if you do the same experiment with an alkaline battery, it'll just get slightly warm. Okay, and that's because that alkaline battery that claims to be 1.2 volts won't be anywhere close to that once you hook the wire across it, because the chemistry will give up. Now, voltage, we've seen this before. It's if we think of how hard it is to actually push charge, get charge moving through air, that gives you a feeling for what we mean by voltage. It's the oomph, the push, the push. Now, it turns out that we can simplify circuits by talking about what's called the equivalent resistance. And what that means is that when you hook up a battery or a power supply to something very complex, like a stereo, the battery or the power supply doesn't really care about the details of that stereo, okay? All it cares about is, what does it look like as far as a single resistor is concerned? In other words, if there's a small resistance, we get a large current through the battery. If there's a large resistance, we get a smaller current through the battery, and the battery just doesn't care, and that makes our job easier. Okay, what we mean is that we can take any complex circuit and we can replace it with one single resistor that we call the equivalent resistance, and that will tell us how much current is going to flow through the battery. So let's work some sample problems. A 3-volt battery is measured to be delivering a current of 1/10 of an amp. What is the value of the resistance to which it is connected? In other words, no matter how complex the circuit, what single resistor would give me the exact same current through that battery? Talk to your neighbor. What resistance would give me that current?
I think you.
Okay.
Yeah.
We can get our answer 2 ways. We can use what I call the maths, and just plug into the definition of R equivalent. And I would just divide the 3 volts by the 10th of an amp, and get 30 ohms. Or I could use my common sense and say, well, the resistance is how many volts I would need to drive 1 whole amp through this thing. Well, if 3 volts is just giving me 1/10 of an amp, that's not an amp. I'm gonna need 10 times that much to get up to an amp. And so I would need 10 times 3 or 30 volts. And so the resistance would be how many volts I need for each 1 amp or 30 ohms. Okay. In short, any combination, no matter how complex, of resistors can be replaced by a single equivalent resistance that will produce the same current for the same battery, same applied voltage. Now, how do we find that equivalent resistance? Well, you probably know from 108, those of you that have taken that class or are taking it, that the easy case is when they're in series. When they're in series, I just, well, think of this flow through the circuit as you know, a flow of blueberries, whatever, blueberry juice. And so pick out one of those blueberries, paint them green and call him Fred. And as he's trying to get back to the other side of the battery, he's got to go through this resistor, and he's got to go through this resistor, and then he's got to go through that resistor. And so the equivalent resistance, it shouldn't surprise you, is just the two added together. And that also makes sense from this point of view. When I add resistors in series, the current has to go through one and then through the other. It's like I'm doubling the length of that resistance, and that's going to double the resistance there, if they're identical resistors. Now, if I have a 5 ohm in series with a 10 ohm, that's going to be a 15 ohm resistance as the equivalent resistance. So there's the rule, and that's easy. That's just that's celebrity Jeopardy sort of stuff. Okay, just add them up. Now let's practice. I've got those 3 in series. What's the current through the battery? Tell your neighbor. See if you can get the answer before your neighbor gets it. Okay. Well, again, if I use the math, my equivalent resistance, I just add them up. They add to 18. I've got a 12-volt battery. I solve for I, and I get 2/3 of an amp. It's that easy. Now it gets more complicated. What is the current through that battery now? What is the current through that battery now? Now, we need another idea before we can answer that question. What is the current in each of those 6 ohm resistors compared to a single 6 ohm circuit? Well, to answer that, you're going to need to watch this demonstration. I have 2 bulbs here that are connected in parallel to each other. In other words, they're connected the same way that these 2 6 ohm resistors are connected. The current has to decide, do I go through this one or do I go through that one? It splits and then comes back together here. And what you see when I hook up the battery is that, oh, this one has a switch. Okay. Which one's brighter? They're the same. Okay. Now, if I turn this one off, watch what happens to the brightness of the other one. Gar nix. Bavarian for absolutely nothing, okay? And that's the way you want your house wired. When you turn off the lights in the kitchen, you don't want things to happen in the front room. They want to be independent of each other, okay? I can unscrew this one and that one doesn't care. I can hit this with a hammer and that one doesn't care. I can disconnect it here and that one doesn't care. And so if I get rid of that second bulb or that second resistor, get rid of it, how much current is going through that 6 ohms? Shout it out. 2, okay? V equals IR, V equals IR. Now, if this bulb is just as bright as that bulb, well, that tells me that I gotta have 2 ohms going, 2 amps going through that one as well. And it makes sense, because why would current choose the left one over the right one? The 2 paths look the same. Okay, and don't be telling me, well, it's gotta go further that way. Yeah, you could have 6 miles of good wire, and that's not gonna make any difference, okay? The paths look the same because they have the same resistance on them, identical paths. Now, if that has 2 amps going this way and 2 amps going that way, how many amps are going through the battery, okay? Now think of it as blueberry juice. Instead of amps, say 2 quarts of blueberry juice each second have to go through this path. 2 quarts of blueberry juice have to go each second go through this path. How many quarts of blueberry juice do I have to bring to that junction every second? 4, okay? So I need 4 amps coming through there. Now, the battery doesn't care about the details. It just knows that it's got 4 amps going through it. What's the equivalent resistance? What single resistor would give 4 amps going through it? 3 ohms. Okay, if I do the math, I get 3 ohms. Okay, so there's where things get tricky. If I have 2 6-ohm resistors in series, that looks like 12 ohms. But if I put them in parallel, it looks like 3. How can adding more resistors give me less resistance? Well, when I add the resistor, I'm also adding a new path, a new opportunity for flow. The example I like to use is that when I was alive at Disneyland, they had a brand new ride. It was the Jungle Bear Jamboree. Oh man, it was sweet. It was sweet. Now, back in the day, Disneyland didn't just let you go on any ride. You bought a ticket book. And in that ticket book, there were A ticket, B tickets, C tickets, D tickets, and the highest ticket was an E ticket. And the E ticket was for the very best rides like the Matterhorn. And if you could talk your little brother into giving you his E ticket, you did it, okay? Now, the Jungle Bear Jamboree was an E ticket ride when it was new. And there was a long, long line of people that wanted to see these. It was a bunch of bears, mechanical bears that could sing and dance and tell jokes. It was amazing. Now, if you go to Disneyland, you can't get anyone go through the Jungle Bear Jamboree. You can't talk a kid into going into that. But back then it was popular, and they had to get a lot of people through that thing, but there was only one set of bears. And when they were done singing, they had to get everyone out of that room. And they did that with 8 doors. Were those 8 doors in series or in parallel? Yeah, if those 8 doors were in series, I'd still be there, okay? They're in parallel so that we could all get out in our own little lane. It's like open up another lane of traffic. Now, it doesn't matter how clogged that new path is. If it's new, it's new. In other words, if someone were to yell fire and we were all racing for the doors here to get out of here, well, what if a trap door opened right there and a rope came down? Would that make it harder or easier to get out of this room? Yeah, I still got the 3 doors. We can still go out there. Maybe not all of us could get through that. This gentleman could, okay? But at least he's not competing with us at that door. Any new path lowers the resistance, makes it easier for flow, okay? It's like opening up a new lane on the highway. And I can see that by adding the resistances in parallel this way, I've doubled, if they're equivalent resistances, I've doubled the cross-sectional area and I've cut the resistance in half. Now, here's the rule. Two paths are twice as easy as one path if the paths are identical. And so the equivalent resistance is R over 2. 10 paths are 10 times easier than one path if all the paths are identical. So I take the resistance of one path and I divide it by 10. But the paths have to be identical to use this rule. The paths have to be identical. Do a buddy check. Check on your neighbors. See if your neighbor's still with us. It's about to get harder.
So now it's half the amount. Divided by the-
Okay. Strap in, folks, because this is going to be the challenging part of this lecture. What if they're not equal? What if I have a 5 ohm in parallel with a 6 ohm resistor? And I'd like to play a little game with you. Suppose along the wall, we had a bunch of boxes, and in each of the boxes, we had a bunch of identical resistors. In the first box, we just had a bunch of 1 ohm resistors. In the second box, we had 2 ohm resistors, 3 ohm resistors, all the way up, okay? And I challenge you to make this circuit, but only open one box. You can only open one box, and you have to make your circuit completely parallel. You're going to put all of the resistors that you pull out of that box, you're going to hook up parallel, and you want to get the same current that you would get with a 5 ohm and a 6 ohm resistor in parallel. Which box do you open and how many resistors do you take out of the box? Talk to your neighbor. Which box do you open and how many do you take out?
One over your box, and get out the lead. I think I would either take out 1, 6. Or I can have 1, 2, 5. I don't know how either of that's possible, but 5, no, not 5. I think that's
Okay, brave soul, raise your hand.
From the 1 ohm box, 11.
What's that?
The 1 ohm box, but 11 ohms.
11 of the 1 ohms would give me, if I had 11, and each of those was 1 ohm, that I don't think would do it. But 11 is the right number. Anyone else? $30 ohms. Excellent. Okay. I would open the 30 ohm box. And why is that? Well, the reason we open the 30 ohm box is because I can make both of those resistors, the 5 and the 6, out of a bunch of 30s. If I wanted to make a 6 ohm resistor, I could make that out of 5 30s. 5 paths are 5 times easier than 1 path if they're all the same. And 30 divided by 5 is 6. Is that right? I can also make a 5 ohm resistor out of 30s if I have 6 of them. 6 paths are 6 times easier than 1 path if they're all the same. And so now when I put those together, what I have is a bunch of 30s. That 5 is going to be 6 30s. That 6 is going to be 5 30s. And the resistance is going to be the resistance of 1 path divided by the number of paths, 11. And that's going to be 2.9 ohms. Now I want you to notice something. 2.9 is less than 5. And that will always be the case. If you have parallel branches, the equivalent resistance will always, every single time, be less than the least resistant path. because you're adding a new opportunity for flow. Now, some of you may have learned a formula for parallel resistors. Tell me if you learned this formula where 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2, spelled with an R. So in this case, that would be 1 over 5 ohms plus 1 over 6 ohms. When I'm adding fractions, what's the first thing I want to do? Yeah, the lowest common denominator. And that's going to be 30. And so I can write 1 over 5 as 6 over 30. And I can write 1 over 6 as 5 over 30. And that's going to give me 11 over 30 ohms. And that's 1 over the equivalent resistance. So that means the equivalent resistance, I flip it upside down, would be 30 ohms over 11. Now, I was taught that formula, and I was even taught how to derive it, but it never spoke to my soul. But this speaks to my soul. I can make a 5 out of 6 30s. I can make a 6 out of 5 30s, and now I've got 11 30s, all in parallel. 11 times easier than 130. See if your neighbor just had an epiphany, just a aha, now you're better people, you're gonna smile the rest of the day.
Another way. Yeah.
Okay. Now remember how we measure voltage. We measure it using a voltmeter. We put it in parallel because we're measuring the voltage difference from A to B. And we just want a little bit of that current to go through the voltmeter. And that should give you the answer to this last clicker question. Which has more resistance, an ammeter or a voltmeter? Okay, we've given you the answer several times during the lecture, so everyone should get this right, which means we all go to Disney World. Last call, get it in. 1, 2, 3. Oh, half of us would go to Disney World. Actually, that's just amazing. That is just amazing. The ammeter I put in series, and I don't want, that's the wrong one. I don't want it to affect the resistance of the circuit. So I want an ammeter to have the same resistance as a wire, negligible resistance. On the other hand, a voltmeter, I want to have a huge resistance so that all the current goes through the bulb and only a trickle goes through the voltmeter. Now, when you go into a high school lab, what you'll find are a whole bunch of brand new ammeters, brand new, bought that semester, and a bunch of voltmeters that came over on the Mayflower, okay? And that's because if you hook up an ammeter wrong, because it has the resistance of a wire, it's like hooking a wrench across your car battery. It just fries it. And so you just go through a whole bunch of ammeters in the course of doing your experiment. But a voltmeter you can only break by throwing it against the wall. It has such a huge resistance that you can hook it up to anything and not hurt it, okay? Now, last question. This will help you with your homework. I have a 1 ohm resistance in parallel with a million ohm resistance. The equivalent resistance is going to be greater than 1,000,000, between 1 and 1,000,000, or less than 1. I lied, there's one more clicker question. And then you can go to the devotional. Okay. Last call. Good. The answer is C. Remember, it's less than the least. I can see that by moving this junction over to the left. And you see that that's a 1 ohm resistor with another path. That's like the trap door in the ceiling. That lowers the resistance. So the answer is less than the least, less than 1. Okay. Have a great day. Good luck on the exam if you haven't taken it already. Most people have been taking an hour and a half, but I would plan on giving yourself a little bit of a cushion.